Okay, so I have a question. What is E? Is that the value E right there? That's an approximation, right? E is like pi. It's an irrational number, has an infinite number of decimal places, right? So when you put, like in graphing calculator or in your handheld calculator, I put an E squared. Let's see, let's get some more decimal places here. Okay. How does it know what E squared is? How does it know what E squared is? Is that a number that it has saved in its memory banks, your calculator? Or the graphing calculator, this program? Does that have E squared saved in its memory banks? E to the 2.11. How does it know what E to the 2.11 is? Partial sums. All right, well, let's think about, so it does not have, there's no possible way. First of all, that's an infinite decimal, right? So that's just showing an approximation. And second of all, there's a myriad of exponents we could put on E that can't possibly have all these values saved in its memory banks, because now I could do 2.0198. Right? It doesn't have those saved in its memory banks. It's doing something to show you that that's an approximation for that number. So what is it doing? Stay tuned, okay? Stay tuned. So last time we were working on this example. We had the function was sine of 1/2 x. And we said the purpose of Taylor series, Taylor polynomials was we want to represent that or reproduce that, construct that, but like in polynomial form, right? In polynomial form. Why? Because polynomials are just easier to work with. They're easier to take derivatives of, integrals of, and they're based on purely on arithmetic, multiplication and addition. You know, sine and exponential functions, they're kind of more complex in what they mean. They're more complex than just basic arithmetic. Polynomials are just arithmetic, so if we might have some applications where it'd be nice to have a polynomial instead of sine of 1/2 x. Okay, so what did we do? We said that polynomial looks something like this. So here's an nth degree polynomial down here. So like this last one here, that would be like an nth degree polynomial. We said in order to figure out what polynomial we could kind of make it be like sine 1/2 x, we would need to find the coefficients, right? We need to find the coefficients, and we did that. We derived the coefficients last time. And we derived the coefficients such that at the center point A, right, at this like focal point A, we tried to get everything right, right? So first we got the function value right? So first we got the first coefficient, so we got the function value right. And so if we pick that Taylor polynomial that's just the first coefficient, that constant coefficient, all we get right is the value of the function at the center point, right? The center point was 1. And so all we get for that basic polynomial of just a constant is just that y value right at our focal point. And then we said, what if we included the next coefficient and the linear term, and made this is a first degree polynomial, right? First degree polynomial. What would that get right? Remember what we said? It would still get the function value right, but it would also get one more thing right. What would it get right? The first derivative right at the focal point. And so then what will that look like? That will be like the tangent line, right? Again, focusing on at x equals 1. We're trying to build a polynomial or polynomials that reproduce our sine of 1/2 x. So if we just use the linear polynomial, it's just going to be correct in a linear fashion around 1. So see, it's really close around 1 there. All right, then say let's step it up. And we said, what if we used a quadratic polynomial? What would that get right? Function value, the first derivative, and second derivative, right? And so only at 1, right? So it gets the function value, the first derivative, the second derivative correct at 1. And then in a neighborhood around 1, now it's starting to reproduce the function. Do you see that? And so as we continue to make a higher and higher degree polynomial, we continue to force more and more derivatives to be correct at 1, which makes a larger neighborhood approximate sine 1/2 x. So here's the 4th degree polynomial. So this is the 4th degree polynomial trying to be like sine 1/2 x, doing a really good job at our focal point. And a pretty good job for now an interval of about 2 or 3. Okay, so these are what are called Taylor polynomials, right? So the higher the degree, the better it approximates the function, and that's centered around our center point, right? And we get a better and better interval for a higher and higher degree polynomial. So looking at those polynomials there, that should remind you of something that we've talked about. So that's that progression of functions. That should remind you of a really important concept that we've talked about in the last couple weeks. C naught, then C naught plus this, then C naught plus this plus this. Was it? Partial sums, right? This is like a sequence of polynomials that's like the same as a sequence of partial sums, right? Where you just keep adding one more when you go to the next term in the sequence. What is the limit of the sequence of partial sums? What did we say the limit of the sequence of partial sums was? What's that? Right. If the series converges, then it's the sum of the sequence of partial sums. Its limit is the same as the sum of the whole series. If we were able to add all infinitely many terms together, the limit of that progression of partial sums would be that sum of all the terms. Like if we could add all infinitely many of them together. Okay, so here's those, right? So starting with n equals 0, we derive the coefficient. Remember we found the coefficient was the nth derivative at a over n factorial. Remember that? Did that last time? So now we can think about, let's make an infinite series, a power series, right? A power series, like an infinite polynomial. So we got the coefficient for the nth degree, then times x minus a to the n. And what that will do is that will just do this. And then just keep adding more and more terms indefinitely, right? So these up here are called Taylor polynomials. These are Taylor polynomials. What do? They approximate the function close to the center value. And if you take the limit of the sequence of these Taylor polynomials, the limit of that is what we call the Taylor series. Okay, so I have a summary screen before we move on. I don't want you to try to, if you want to take notes on this, pause the video later. Just listen. We'll just go through the summary screen, but I don't want to go through it so that you have time to write it all down. If you want to do that later, please do. So here we go. What is our goal? Our goal is to write a non-polynomial function as a polynomial. We call the non-polynomial function, I've been calling that f, and a polynomial capital T, okay? They're the most convenient, okay? They're the most convenient to work with. And so here was our Taylor polynomial, right? Our nth degree Taylor polynomial shifted to be centered at A, right? Just all it is a polynomial. What makes a function a polynomial? Make sure we get this right. It's going to be on the test Friday. What is a polynomial? Is sine polynomial? How about x squared times sine? Is that a polynomial? No. Polynomials are of this form. Coefficient times x to a power plus coefficient times x to a power plus coefficient times x to a power. Those are the only, that's what a polynomial means. It never involves sine, cosine, e to the x, right? It's all based on multiplication and addition. Coefficient times x to a power plus coefficient times x to a power. That's what a polynomial is. Okay? So first thing we said was a Taylor polynomial estimates f, and I could say close to a, right? Close to a. And the accuracy of that depends on n, how big of a degree we pick. Okay? Centering at a means the first n derivatives are exact, I should say at a, I should say. Okay, writing the Taylor polynomial means determining the coefficients. We derived that last time, the nth power of a over n factorial. Those are the coefficients that we use to construct this polynomial. Okay, the sequence, this is what we just talked about. The sequence of Taylor polynomials are better and better approximations of f, and each one gets one more derivative at x equals a correct. Okay? And then the limit of the sequence is then a Taylor polynomial with an infinite number of terms, which we know is a power series, right? That's just a power series. Power series is like a polynomial with an infinite number of terms. And this particular type of power series is called a Taylor series. Okay, so here is the Taylor series. All infinitely many terms, n equals 0 to infinity, of our coefficient, x minus a to the n. Okay. Again, that's on the video if you want to slow it down. Let's see. I guess we're... All right, so then this is all we just wrote. So then this new fact is what's called a Maclaurin series, okay? Maclaurin series, it's like the easiest case of a Taylor series. That's when your a value that you're centering about is 0. So if you have a Taylor series, and if you choose your center point a to be x equals 0, then that has a special name called a Maclaurin series. So what I want you to do is, I want you to write the general form of the Maclaurin series, both in sigma notation, and then what it means. So write the general form of the Maclaurin series. If what it is, it's a Taylor series centered at x equals 0. That's your a value. All right, so write the general form of the Maclaurin series as a sigma form, and then write it as an expanded sum. Go. Go, did you get it? No. How about Riddick, did you get it? Tell me. N equals 0 to infinity, good. The nth derivative of f. At where? Okay, so the whole point of this was the Maclaurin series, what? Is this centered about x equals 0. So the nth derivative of f taken at 0. That's the whole point. This is the whole point, right? That a is 0 for a Maclaurin series. That example we just did, it was centered at 1. Everything was centered around 1. Maclaurin series, everything will be centered at 0. That's what it is. It's a specific type of Taylor series centered at 0. You want to keep going? Okay? So what will it be? If you simplified it, what would you get? X to the n. So this is actually like easier, right? It's easier because 0 is oftentimes easy to work with. Instead of x minus a number to the n, we get x to the n. Okay, and so then you see this and you think what, right? You see this and you think what? Yeah, Penny.
So as expanded, just coefficient, then plus coefficient 1.
And, okay.
Or should I just write?
Yeah, so let's go ahead and do it. So
in that case, I just do f of 0 to the, 0 over 0 factorial.
which is?
1.
And
then x to the 0.
which is? So?
So it's just f of 0.
Good.
The coefficient. And then the next one would be f of 1 to, f of, to the first derivative.
Right?
0 over 1 factorial, which is 1 again.
Right.
Times x to the first, which is just x.
Right.
And then you just keep going, following that pattern. So you get f to the second derivative of 0 over 2 factorial, which is 2. And then x squared.
Right. All right, I want you to, okay, and then where do we stop?
So we go to the nth derivative.
We're going to stop at the nth derivative?
No.
Do we stop at the nth derivative or not? If we stopped at the nth derivative, what would we have?
Just up to that nth term.
And what would that be called? If you ever stop, then you have, what do you have? You have a partial sum, or one of these is a polynomial, just a plain polynomial. In this case, it would be called a Maclaurin polynomial, right? So we've been focusing the last day and a half now on Taylor polynomials. Those are partial sums of the Taylor series. So if you ever stopped, you'd have a Maclaurin polynomial, a partial sum of the Maclaurin series. So I want you to write the second degree Maclaurin polynomial. Write the second degree Maclaurin polynomial. Or do something on your paper to indicate what is the second degree Maclaurin polynomial. Jamie, what do you think about that? She wants the first 3 terms. Agree? Is it just this term? Is this the second degree Maclaurin polynomial? No, it's the partial sum up to a second degree. So this is right. This is the second degree, or quadratic, right? Quadratic Maclaurin polynomial. What does it get right? Kenny knows. What does it get right? Samantha.
So the value of the function first derivative is
Where? Good.
at 0.
At 0. What does it get right? It gets the value of the function, gets the first derivative and the second derivative right at 0. And then what else does it do? Around 0, it's what? Exactly? Right?
Pretty
Close, right? So near 0, it's going to be close. You get far away from 0, and it's going to do something else, right? It'll be a parabola. It won't be, whatever the f function is. Okay, any questions on that? Does it make sense? So let's look at e to the x. Question? Sure.
So is there, so if we are to write the Maclaurin series, is there an end term that we have to write, or no? It's just the dot?
So if it's the Maclaurin series, what does it mean? So how many terms do we add together? Infinite number of terms. Yeah. Yeah, so if you're expressing it as an expanded sum, you have to just write dot, dot, dot. You can't show a final term. So as soon as you show a final term, that's a Maclaurin polynomial, right? You stopped, right? The series will be the infinite series. Okay, so what we're going to do is we're going to build, it's the PowerPoint, we're going to build the Maclaurin series for e to the x, okay? So here's what we just wrote, right? So we're going to build that Maclaurin series for e to the x. Nice, easy one to start with. So what I recommend to do that is let's make a table, because what we're going to need is, for the Maclaurin series for e to the x, we're going to, basically all we need is we're going to need all the derivatives at 0. If we have all the derivatives at 0, then we can write the coefficients and we can write the Maclaurin series, right? So let's make a table with n values. And then we'll do the first derivative before we plug in 0, and then we'll plug in 0 to those derivatives, right? And then we'll have the derivatives at different derivatives at 0, and then we can set up the Maclaurin series, right? Okay, so first the nth derivative is just the function, right? So, or sorry, the 0th derivative is just the function. What function are we doing? E to the x. Okay, and then we can say, what is the function evaluated at 0? 1, right? Okay, second derivative, or sorry, first derivative, right? So the nth derivative would be the first derivative. So what's the derivative of e to the x? E to the x, evaluated at 0? 1. Second derivative is the first derivative of e to the x. This one. It's the first derivative of the first derivative, which is? All right, so very quickly we're seeing that all our derivatives are going to be e to the x. All of them evaluated at 0 are going to be 1. Unfortunately, it's not always that easy, okay? But so now write the Maclaurin series for e to the x based on this. You've got, what do we find? All the derivatives at 0 are simply 1. Here's our general form of the Maclaurin series. So I want you to write out the Maclaurin series for e to the x. Can you do it? Get it? So you said 1 plus just 1? 1x, right? Plus 1/2 x squared, good. What do you guys think? You getting it right? And then if it's a Maclaurin series, then it just keeps going like that. And so this would be, we could write the general form as. So how could we simplify now the general form? Get that? So how could I write this for e to the x? Yeah, so it just ends up being x to the n over n factorial. Okay, so now there's a question of convergence, right? So this is a power series. And what do we ask about power series? We asked, for what values of x does the series converge? All right, so we know for sure it's going to converge at 0, right? Because this forces everything to be right at 0. But then how wide of an interval around 0 will it actually converge to e to the x as we let n get really, really big? So how do we find the interval of convergence for a power series? Ratio test. Let's do it fast. Ready? So x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. We're looking at that absolute value. So I'm doing this fast because so we got x, basically x over what's n factorial over n plus 1 factorial? Just an n plus 1 in the denominator. That goes to what as n gets very big? 0. So for what values of x is our ratio less than 1? What values of x will make that ratio's limit less than 1? All x, right? All x. So this Maclaurin series will converge to e to the x for all values of x, from negative infinity to infinity. Well, that's the best we can do, right? That's a great Maclaurin series because it actually reproduces e to the x perfectly if you could add all infinitely many terms together. All infinitely many terms of the polynomial will reproduce e to the x perfectly for all x. All right, so I want you to just determine, point out, write down the first degree Maclaurin polynomial for e to the x. What's the first degree Maclaurin polynomial for e to the x? Lily, what do you think? What is that? 1 plus x? She wants this. That's the first degree Maclaurin polynomial. Right? Yep. What does it get right and where? What does it get right and where? Does it get exactly right?
Function value of 1 and the first derivative.
At where?
At 0.
Right. It's going to get the function value right at 0 and the first derivative right at 0. And then maybe for a small neighborhood around 0, it's going to be a good approximation of e to the x, but only a small neighborhood, right? We know eventually it's going to be all x, right? If you get enough, you get all the terms. But just the first two terms is going to be a weak approximation, except for really close to 0. Okay, so let's look at this. Let's look at some graphs here. Any questions on that? So here is, I thought, what did I do? Oh. So there's e to the x. And what does this represent? This represents, is this the Maclaurin series? Is this the Maclaurin series for e to the x? What is it? What would that be? What would you call that? What's that? Right. Right. It's a partial sum of the Maclaurin series. And what do we call that? Partial sum of the Maclaurin series. Maclaurin polynomial, right? It's a finite number of terms. So let's return to our question of e squared. We asked the question, how does like your handheld calculator or say my program here, how does it come up with this number when I put e squared? How does it do it? All right, he said a second degree Maclaurin polynomial. Let's take a look. So what do you expect the 0th degree Maclaurin polynomial to look like? I'm going to turn on the 0th degree, the graph of the 0th degree Maclaurin polynomial. What will that be? What's that?
1.
Okay. And as a graph, so how would you describe the graph?
Horizontal line all the way across.
Right. So there's the 0th degree Maclaurin polynomial. What does it get right? Just the function value at 0, right? Just the function value at 0. Okay? What do you expect to see when I turn on the first degree Maclaurin polynomial? The tangent line, because it gets right what? It gets the function value and the first derivative. So you're going to get you basically get the tangent line. Second degree. So the second degree Taylor polynomial is, we call that T2. And what is it? So let's write out the second degree Taylor polynomial. What would it be? Jennifer, what would that be? Right? Right? Good. And now I'm showing that in the purple graph, the pink graph. So I asked the question, how does the calculator calculate e squared? And so someone offered up, it uses the second degree Taylor polynomial. So how, if that were right, how would it use the second degree Taylor polynomial to calculate e squared? What would you do with this to get e squared, or an approximation of it? What would you do?
Center it on whatever your x is.
So we're already centered on 0. So we're centered on 0. That's what this is. It's centered at 0. But now I want to use that polynomial. So I think you're thinking the right thing, but you don't want to. It's already centered at 0. What are we going to do with that then to approximate e squared? Right? So this is an approximation of e to the x, and if I'm interested in e squared, what will I do? It's not centering. We've already centered at 0. Yeah, you just evaluate this at 2. So I think that's what you're thinking, but don't say center it, because this is centered at 0. It's never going to be anything but centered at 0. But now we're going to use it, but it's giving us values for lots of x values, even though it's centered at 0. See? I get y values for all x here. So then what I want to do is I want to look at t. I want to look at this second degree Taylor polynomial evaluated at 2. And so what will that be? That'll be 1 plus 2 plus 1/2 2 squared, which is 5? No? Yeah? Is it 5?
It is.
This doesn't, is this? Oh, I guess it is. Okay. So we get 5. Is that how it's computing e squared? All right, so no. So what is it doing? Or maybe, so I should, a little caveat here. I'll say that at the end. So what is it doing? What is it doing then if it's not the second degree Taylor polynomial that's helping us? What instead? Andrew. The infinite term?
I don't know how to. It's taking it to.
Well, you said it first. Far enough out.
Just taking it far enough out.
Far enough out. So the second degree. So here's, this is showing right here. This is showing what the second degree polynomial thinks e squared is. What is e squared actually? Up here, the 7.389 something, right? So this is the true e squared, or really close, really close. And then this is the second degree Maclaurin polynomials version of that, plugging 2 into that function, right? So let's look at a better Taylor polynomial, Maclaurin polynomial. Here's the third degree. So this is showing here, this is showing whatever degree we're on. So this is the third degree Maclaurin polynomial evaluated at 2. It's 6 1/3. Okay, here's the fourth degree. It's 7. So we see it's getting better. So the purple graph, again, this is now the fourth degree Maclaurin polynomial for e to the x. And you see it's centered at 0. It's doing a really good job, close to 0, of approximating the function. And it's getting the first 4 derivatives perfectly correct at 0. All right, so here's the fifth, 6th degree, 7th degree, 8th degree. Here's the 9th degree. What do we think? Is it the 9th degree?
Oh, close enough.
Close enough for the display? What does it get? No, but so how is it? But no, but the point is, how is it giving us this good of an approximation? Is it the 9th degree? No, that only gets what? That gets like the first to the nearest 100th. So let's try, I think I got one more here. 10th. Here's the 10th. Again, the 10th is maybe getting it to the nearest 100th or 1000th or something. So what should we try? Let's try. Let's put in n equals 15. Well, the limit then would take the calculator an infinite time to do, right? It's only gonna do a finite sum polynomial that gets enough right. How about this? 15th. Does it do it? Almost. Should we try 16th? 16th. Got it. So imagine so the T16 would be 1 plus x plus 1/2 x squared plus dot dot dot. What would the last term be? X to the over 16 factorial. So this Maclaurin polynomial is good enough at x equals 2 to get e squared, e to the x, correct to whatever number that 9 decimal places? 9. 9 decimal places. All right? So my point is that this stuff is entirely applicable, right? Entirely hugely important in how computers calculate values like irrational numbers. Okay? They use so this whole time I've been saying this is what it does, okay? It might be something similar to this, okay? But this is what's called a numerical method. This is what's called a numerical method. A numerical method is how a machine or a computer will come up with a good enough approximation so that you look at it and you think it's exact, or this is perfect, right? So a numerical method is similar to building a Maclaurin polynomial and taking enough terms so that if you want it to 9 decimal places, it'll give it to you correct to 9 decimal places. Okay? That's how calculators do calculations. They use numerical methods like Maclaurin polynomials and Taylor polynomials. Yes, ma'am.
So if you didn't take e to this e squared
Right.
out like 9 decimal
Yep.
places, it would have taken you a smaller degree,
Yeah, like if I'm here in my calculator program and I say,
like 4 to
yeah, say instead of 10 significant digits, I only want 4. Then maybe to save some thinking and computing time, maybe it would only take it out to the 12th or something. Let's see if 12 does it. 12 does it. Does 10 do it? Even 10 does it. Does 8 do it? 8 doesn't do it. So yeah, maybe to be more efficient, if you tell it, oh, I only want 4 significant digits, it would do something easier, right? Yeah. Imagine if you had a computer running lots and lots and lots and lots and lots of calculations for a long period of time. That would be helpful for efficiency, right? Okay, does that make sense? So this stuff is highly relevant, right? We've got machines all around us computing values in all fields of science and mathematics, right? And so how does it do it? It uses things like Taylor and Maclaurin polynomials to get whatever approximation that you want. So it may feel like a lot of symbol pushing, but it's super important, right? That's how your calculator works. All right, so let's work on another one that's a little bit harder. Let's do the Maclaurin series for cosine x. So build your table. I'll take attendance. Build the Maclaurin series for cosine x.
power. That's the, yeah.
Okay, check your work. This is what I got. Or check my work, maybe. Maybe I made a mistake. What do you think? So I got, for my derivatives, I got 1, 0, negative 1, 0, 1, 0, negative 1, 0 for the derivatives. And then if I put it into our Maclaurin series, I got 1 plus 0 minus x squared over 2 factorial plus 0 plus x to the 4th over 4 factorial plus 0 minus x to the 6th over 6 factorial etc. Do you follow? Did you get that? Some nods. Okay, so here's what. So that's if you kept going, that'd be the Maclaurin series for cosine. So a couple of things to talk about. For what values of x does it converge? So what we would run, we would have to come up with a general. We'd have to come up with some formula for that and run the ratio test. We need the general term to do that. So we don't have that yet. So we need the general term. We need to run the ratio test. And then another thing to consider here is if every other term is 0, could we rewrite this with a new indexing system, right? To get rid of those zeros. So like a new index system, say j. So when j equals 1, I get 1. And when j equals 2, I get the next non-zero term. And then when j equals 3, I get the next non-zero term. That would be nice, right? Instead of having these zeros. So we like re-index it so that j equals 1, 2, 3, 4 gives us all the non-zero ones. And then if we could get that general term, then we could run the ratio test and find out for what values of x it converges. And we'll do that on Monday.